A diffraction grating consists of a large number of equally spaced narrow slits and are created by etching thousands of thin lines onto a glass slide. They produce maximum and minima just like in the double slit experiment. Here's the graph we had earlier. You can see the maximum lines, the maximum intensities, and the intensity falls off very smoothly. But the pattern is much sharper because instead of just two slits in the double slit, I have thousands of slits in the diffraction grating. The more lines or slits there are, the narrower the peaks are. Also, if we were to shine white light on a diffraction grating, we'd get a spectra of all the colors. Since, as we're about to find out, the location of maxima depends on the wavelength, and the colors in white light separate out, just like dispersion, which we showed earlier when we were talking about prisms and rainbows. Here are two examples of what a diffraction grating will show. If we put a diffraction grating up and we pass through the spectra from excited xenon gas over here, we will get very discrete lines here. You can see the green lines here, blue, violet, red, very discrete patterns. If we were to pass through white light like from the sun, we will see all the colors and they'll be smeared together. You can also see this effect by looking at a CD, if you have any anymore, or a DVD at an angle, because they're created by etching cuts into a polycarbonate plastic disc. When you do the math, you come up with the equation for the maxima for diffraction grating is the same as for the double slit experiment, where we have m is the order, lambda would be the wavelength of the incident light, L is the distance between the two observation screens, and D here is the distance between the individual etchings. Of course, with a diffraction grating, this is much smaller than the distance between the two slits in the double slit experiment.